Hello, Cal2. Last time we were talking about polar coordinates when my internet flaked out, and I'm going to pick up from there. So we saw that polar coordinates are an alternate coordinate system. Instead of an x-coordinate and a y-coordinate, you have an r-coordinate and a theta-coordinate. R is distance from the origin, theta is angle to go in or go against, depending on whether your r value is negative. You're allowed to use positive and negative r values. It's not unique the way rectangular coordinates are. A point only has one x-coordinate, but you can express its theta value in infinitely many ways. You can express its r value in two different ways if you're letting yourself use negative r values, and we traditionally do. Let's say some equations. If you wanted to go from polar to rectangular coordinates, so I know my r value and I know my theta value. Well, if you took a calculus class, then it's pretty easy to work out how you get from here to there. It's x is going to be r cosine theta, and y is going to be r sine theta. This will be x, this will be, or that'll be r, that'll be x, that'll be y. So sine theta is opposite over hypotenuse, gets you there. Yeah, this is the easy direction. The other direction is the hard one, going from rectangular to polar. We know it's going to be hard because we know that there are infinitely many possible solutions. So it's not going to be something where we just solve for theta, or I guess we could, but that's a pain to write. If you want to go from rectangular to polar, the usual way to express it is think about y divided by x. The r's cancel, and you get sine theta over cosine theta. So y over x equals tangent theta. We could go a step further and say that that means theta is tangent inverse y over x, but that's only going to give us one of the theta values, so we don't usually write it like that. If you hand me a specific y and x and ask me to find a coordinate, that's probably the thing I'll do, but we'll both be aware that there are other possible solutions, and this is the step where I could have branched off. And then r is easier. R squared equals x squared plus y squared. Again, you might want to solve for r and say that makes r the square root, but it might be the negative square root. So, yeah. Let's do an example using this. If I hand you r equals negative 2, theta equals negative 5 pi over 6, and I say write this in rectangular, that's easy. I'm just sticking these points into this formula. X is going to be r cosine theta. That's negative 2 cosine negative 5 pi over 6. Oh geez, where's negative 5 pi over 6? This is 30 degrees here. So cosine theta will be negative root 3 over 2. So I'm getting negative root 3. My y coordinate will be negative 2 sine negative 5 pi over 6. Looks like that's negative a half, so I got negative 2 times negative a half. I get 1. 1? What's going wrong? Oh, I forgot the negative sign. What? Yeah, that's what's wrong. This was a negative sign. That makes this positive. My r value being negative is spinning my point up into quadrant 1, so I'm expecting a positive x and a y coordinate. My theta said go this way, and then r said, and after that turn around. So, yeah, that makes sense. Yeah, let's try doing the opposite direction, which is the one that's a pain. If I hand you the point, 2 comma negative 3, and say write this in polar coordinates, in 3 different ways. Okay, I know tangent theta is y over x is negative 3 halves. I know r squared equals x squared plus y squared. That's 4 plus 9 is 13. So I want to jump out and say, well, that means theta is tangent inverse that, and r is square root of that. And that usually does give you one of the things. But I want to think about the quadrant and double check that I'm using the positive or negative correctly. 2 comma negative 3 puts me here. If I think about tangent inverse of negative 3 halves, tangent inverse looks like this. It goes from negative pi over 2 to pi over 2. Tangent inverse of a negative number will give me something between 0 and negative pi over 2. I'm ending up in that direction. Good, that's where I want it to be. It's worth noting, if my point is in this quadrant or in this quadrant, tangent inverse is going to give me the wrong value. Like tangent inverse gives you the value in quadrant 1 or 4, whose tangent is that. There are multiple angles with the same tangent, so yeah, you're going to get wrong things sometimes. So yeah, this does work. Tangent inverse will give me an angle that's pointed at the point, so r should use positive root. I can say theta equals tangent inverse negative 3 over 2. This isn't one of the numbers that's on the unit circle, tangent inverse, so this isn't some nice rational multiple of pi, unless there's something I'm missing going on. R is root 13. There's one way of doing it. I could take that angle and add pi to it. Here's a new theta value. So now I've taken it and swung it around here. If I want to use that angle, then I need to swap r with its negative. R is going to be negative root 13. Or I could take theta equals tangent inverse negative 3 halves and add another pi to that. Now I'm back to the same orientation. And now r should be positive again. Here are 3 ways of doing it, like they asked for. Cool. You can graph stuff in Polar. You can find graph paper in Polar. I don't have a template for my journal writing thing, but you can Google some Polar graphing paper. Let's graph a couple easy things. Let's sketch r equals 2. While I'm doing this, I might think in mind, what does x equal 2 look like? If I graph x equals 2 in rectangular coordinates, that's a vertical line. If I graph y equals 2 in rectangular coordinates, that'll be a horizontal line. So I'm thinking about what would a vertical/horizontal line be in Polar. If your r value is 2, but your theta is allowed to do anything, here's theta equals 0, whose theta is pi over 2. Here's theta equals pi. Here's theta equals 3 pi over 2. You end up with a circle. Circle is like the vertical line for polar coordinates, or maybe it's the horizontal line, depending on which of you think of as the x and which you think of as the y, which again is a nightmare that we can't get it straight. Let's sketch theta equals pi. Let's make it pi over 4. Sketch theta equals pi over 4. You will be tempted to just do this, and that's part of it. Here's a question: should you include 0, 0? You basically always include 0, 0 because if I use the point theta equals pi over 4, comma r equals 0, that does give me the origin. R equals 0 is a point that's hit by every angle. But also remember, you're allowed to use negative r values, so you get this part of the line too. You get the entire line for that theta value. Let's try sketching something a little more interesting. Let's sketch the equation r equals 2 cosine theta. I'm going to pull out a graphing calculator to graph this with in a second, but I want to try doing this by hand. Let's think about plugging in some values. Theta r. If I use theta equals 0, I get an r value of 2 cosine 0. Cosine 0 is 1, so I get 2. If I want to have an angle of 0 and an r value of 2, that puts my point right here. There's my theta equals 0 value. If I go up to theta equals, let's try pi over 4. That's one I can do. Cosine pi over 4 is root 2 over 2. So I get root 2. My key thing I'm imagining is I've got in my head what this is r equals 2 and this is r equals 1. We're going out to root 2, which is somewhere between 1 and 2. It's like 1.4. I'll put it like here. Theta equals root 2. No, theta equals pi over 4. It's somewhere around here. I could get exact coordinates. I don't care about that too much right now. I'm just trying to get a sketch. If I go up to pi over 2, now I'm going vertically. My r value is 2 cosine pi over 2. Cosine pi over 2 is 0, right? Yeah, x coordinate is 0. So I want to go this direction by 0. That's easy. That gives me this point. Cool. Cool. Let's jump up to 3 pi over 4. This time I get 2 times negative root 2 over 2. Now I'm at this angle. Cosine that is negative root 2 over 2. 2 times that is negative root 2. So I want to imagine moving this direction by negative root 2. Again, I have in my head, here's 1, here's 2. I want to move at the 45-degree direction, somewhere between 1 and 2. 1.4 will put me somewhere around here. So keep in mind, if I'm following my dots, I went like this, and then I went like this. Here's a thing you're going to be tempted to do. Here's the easiest mistake you make when you're graphing something in polar. You're going to be tempted to approach this point at some angle. Like, think about what is the slope that I hit that point at. If I think about the slope for a second. The con is that all of the angle this thing intersected us at theta equals pi over 2. If you hit this with a slope of 1 or something, then all these angles between there and pi over 2 don't have a point to go with it. So you automatically know, by virtue of the fact that you used all the points, all the angles, all the way up to pi over 2, means that no matter how steep I draw this line, there are points in there. We must approach the point 0, 0 with a vertical tangent. You can often get for free that you approach things with a vertical or horizontal tangent or whatever. Because we came into this from pi over 2, we must be headed straight downwards through pi over 2. And the same deal after this. We come out of it at a vertical tangent also. Because we're not going to miss any angles between pi over 2 and a little bit bigger than pi over 2. We need to know that no matter how close your angle is to pi over 2, there are points down in there that are part of the graph. 3 pi over 4 puts us there. I want to connect those dots. And if I go up to pi, I get r equals 2 times cosine pi is negative 1. I get to negative 2. Well, that's this point again. So my curve is crossing itself here. And it's not immediately obvious right now, but if I plug in some points, I can work it out. If I go to, what'll be the next pi over 4 after pi is 5 pi over 4. I'm going to get r is 2. What is cosine 5 pi over 4? It is negative root 2 over 2. It gives me negative root 2. So I want to go this direction by negative root 2. Puts me back at the exact same point I was at before. Going this direction in the opposite way, like I was moving at an angle of pi over 4 to land on root 2 here. This is the opposite angle, and the opposite distance puts me at the same point. And all of these points are going to be the same point again. When I go from 0 to 2 pi, which is my normal thing I would do to get a full trace of cosine, I'm going to end up tracing this graph exactly twice. I will go through it once, and then I'll be back where I started and go through the exact same points again. This is a thing that happens a lot in polar that you kind of want to keep in mind of. Like if I was trying to compute the arc length of this curve, for example, I would need to keep in mind to not go from 0 to 2 pi, which would be the default, only go from 0 to pi, because I don't want to trace the arc length twice. This is often the trickiest thing going on in polar coordinates, is figuring out when it overlaps itself in junk. Here's one of these places where I kind of graphed the thing too well. Like, I've got this goofy closed shape that I drew it so that it looks like a circle, and surprisingly it turns out it is a circle. Let's try graphing polar real quick here. So I need to go to mode. This is the place where I told it to do parametric graphing last time. I'm going to tell it instead go to do polar. And the function I want you to graph is 2 cosine theta. This button xt theta n will do different things depending on what you got. If I set my window to include x values from, I guess I want some negative y values. Let's go down as low as negative 1.5, up as high as positive 1.5. Can I see everything now? The aspect ratio is not perfect, but yeah, this thing comes out to be a circle. Weird. I guess I haven't convinced you that it's exactly a circle. It's definitely circle-y looking. Let's try this in Desmos, which gives better, prettier pictures. Dear Desmos, how do I need to Google this? Ooh. I can get it to do that. Turn that graph off, turn that graph off. If I just type in r equals 2 cosine theta, will it figure that out? It did. Cosine. Do I have a theta? Do I need a space? Can I just type in theta? If I hit X, will it do anything? Nope. Theta. Hey, there we go. This graph makes it way more convincing case that, yes, that is definitely a circle. I could put my cup on it and it'll be exactly, trace it with something circular. It looks circly. How come this is a circle? What's up with that? We converted points back and forth between polar and quadratic, but we haven't talked about converting equations between polar and rectangular coordinate systems. This is a thing that shows up a bunch of times in the homework. Remember, we had some formulas written down. We had that r squared equals x squared plus y squared. Y over x equals tangent theta. These are the ones we used when we went from rectangular to polar. And the other direction was it's x equals r cosine theta. Y equals r sine theta. These are what we had when we were going from polar to rectangular. Well, how do I use that to change r equals 2 cosine theta? Let me point out first a bad way to do this. Like, the worst thing you can do is just try and solve this for theta and then plug that in for theta. Theta is tangent inverse y over x. I guess it's not the worst thing you can do. There are worse ideas. R becomes the square root of x squared plus y squared equals 2 cosine of theta becomes tangent inverse y over x. And now try and simplify that. I guess you could try and simplify that. Maybe you'll have some fun. I don't think that's a good way to do it. By and large, you don't want to use these versions of the equations at all if you can possibly avoid it. Like if you have an r squared, go ahead and use that, but you don't want to do this square root because you're actually not sure if it's a plus or a minus. And once you have the plus or a minus, now I have like 2 copies of the circle floating around or something. Like, thinking about which version of tangent inverse you have and whether you want the plus or minus is manageable when I'm doing it for a point. It's a pain if I'm doing it for an equation. How can I get around this? Think about multiplying both sides by r. When I have a cosine theta, I mostly want to say, hey, that's almost an x. Can I fix it and make it an x? So I multiply both sides by r. You should have a minor alarm bell going off in your head saying, wait, am I allowed to multiply both sides by r? Multiplying both sides of an equation by 3 is totally safe, because 3 is never 0. If I multiply both sides by r, I'm introducing an extraneous solution, because if r was 0, maybe I'm taking an equation that wasn't true and making it true. I'm changing the truth value of the equation at some point. And that's bad. I don't want to add extra points. I can make myself feel better about that by noting that r equals 0 isn't infinitely many points. It's only one dot. There's only one point where r equals 0. That's the origin. And hey, look, the origin is already part of the graph. So I'm not adding an extra point. That point was already there. R equals 0 was already a solution. I can multiply both sides by r. And even if r was 0, I'm making an equation true. That version of the equation was already on the graph, yeah. What does this turn into? R squared can become x squared plus y squared, no square root necessary. That's nice. R cosine theta is x. X squared plus y squared equals 2x. It's not immediately obvious that this is a circle. If I subtract the 2x from both sides, I get x squared minus 2x plus y squared equals 0. I do completing the square and add a 1 to both sides. That becomes x minus 1 squared plus y squared equals 1. General equation of a circle is x minus a squared plus y minus b squared equals r squared. This is a circle with center AB, radius 1. So this is a circle with center 1, 0. Whose radius is 1. Or here the radius is r, here the radius is 1. This is r, not 1 on the general version. Which, yeah, corresponds with what we said. Like, look at that picture. The center is 1, 0. The radius is 1. Cool. It actually is. It's not just kind of circly. It is actually a specific circle. Neat. Let's try doing another sketch. Do I have the homework pulled up? I want to make sure I don't. My notes have problems in them, but I'm too dumb to keep track of. Did I write that down because I was putting it in the homework? I don't want to do the exact problem from the homework. Give me just a second here. Course content, homework. Did I already have this open? Yep, I have 3 copies of it open. Great. So convert to polar, convert back. I don't have enough sketching things. Oh, yeah, the sketching things are problem 143. Sketch this goofy junk. Ooh, these are weird. Cool. Let's try sketching sine 2 theta. Ooh, okay. Let's sketch r equals 1 plus cosine theta. Uh-huh. Adding 1 to cosine theta is nice because it means you no longer have negatives. Sketching these things when r is negative gets weird. Let's think about the simplest values. Let's go 0, pi over 2, pi, 3 pi over 2, up to 2 pi. Cosine 0 is 1. 1 plus 1 is 2. So at an angle of 0, we should go at a distance of 2. Check. If my theta value is pi over 2, so that's vertical, cosine pi over 2 is 0, r is 1. Check. If you go out to pi, 1 plus cosine pi, cosine pi is -1, 1 plus 1 is 0. Ooh, check. 3 pi over 2, cosine of that is 0, so I get 1 again. So now I'm at this direction, go 1, puts me here. And then 2 pi gives me 2 again. Cosine 2 pi is 1 again. So I got these points. What is going on here? It's really helpful to picture these circles. Let me get a light color to do these in. Okay, so from here, theta equals 0 to theta equals pi over 2, we're smoothly decreasing from 2 to 1. Cool. What's happening after that? I'm picturing these angles here. These angles are giving me numbers that decrease from 1 down to 0 slowly. The tricky thing going on here is as I decrease down to 1, it's going to be so tempting to draw myself approaching this point at some angle. Approaching it at some angle doesn't make any sense because what values am I getting between here and here? The function still needs to exist between all the way up until pi. So that angle I am coming in at, when I come in for a landing, I need to be coming in for a landing from a horizontal tangent because I need to get under all of those lines for these angles to exist. And then something goofy happens. I bounce off that point and come back out over here and do the same thing over here. This is not a very good sketch. I'm doing my best here. I get this graph. This graph is called a cardioid. Why is it called a cardioid? Because it's shaped like a heart if you turn your head sideways. Oh, isn't that sweet? 1 plus cosine theta looks really goofy. Let's try sketching this. Do I have my Desmos here? Cosine theta looks like this. It's the same circle, but only half as big. If I add a little bit to that, that's not what I meant to type. Let's put the plus 0.1 on this side. Plus 0.1. By adding a little bit, I'm sort of perturbing the double loopiness of it going on. So now one of my loops is a little bigger and one of my loops is a little smaller. Doing this is kind of a nice way of showing off that, like, even if I was just sketching r equals cosine theta, I might add a 0.1 or a 0.01 to show off that actually there's two loops happening there. If I wanted to conceal the fact that, or 0.01, maybe 0.05. What's 0.05 going to look like? Yeah, it's a little bit off so that the two loops become distinguishable and you can see more clearly that it's tracing the same thing out twice. I want to know what happens as I increase that theta value. From 0.1 to 0.2 to 0.3, 4 to 0.5 to 0.6 to 0.78. So the little loop is getting smaller and the number of angles that it represents is getting smaller. To 0.98, so now we're almost at 1. And when I get right at 1, I get the cardioid type thing. So like this is like a loop that has shrunk down to 0. When I delete that and change it to a number slightly bigger than 1, so here's 1 exactly, is the perfect cardioid. When I increase that a little bit bigger than 1, I can't see anything yet. Let's make it 1.1-ish. I can see how like that steepness goes away. And if I keep making it bigger, the thing sort of flattens out. As the thing gets bigger, I get this big number plus cosine. The cosine becomes less relevant to the big number. It gets closer and closer to being circly. Here it's not that circly because I'm way out here and I'm way down here. If I make the number like, let's make it 10.8. Now cosine is way smaller than 10. This is almost just a circle. It's off by a little bit because the cosine is shifting it to the right a little bit. That's fun to think about. So, yeah, it's worth noting for a cosine or a sine, I know it's going to repeat itself every 2 pi. There are many goofy versions of a sine or a cosine where it doesn't have that. I've asked you to sketch sine of 4 pi over 3. If I plug in 2 pi, it's not necessarily going to be where it started anymore. So I might need to go beyond the regular 0 to 2 pi interval that I would normally graph a trig thing under. I got all sorts of... You can come up with some pretty graphs in polar coordinates. I gave you 3 to graph. Try and do the first 2 by hand. Go ahead and just stick the third one into a thing. But play around. There's all sorts of goofy stuff you can do with graphing in polar coordinates. Get all sorts of funny flower things. If you ever had a spirograph when you were a kid, you're getting the kind of things you graph with a spirograph. Let's see. A good thing to keep in mind is that a polar graph, if you've got r as a function of theta, let's grab a baby one. Let's sketch r equals theta squared. Here's one where there's no trig going on at all. What do I get from this? Well, at theta equals 0, I get 0. And as my angle increases, my r value is going to increase from 0. So I've got the same horizontal tangent phenomenon I had a second ago. That because the thing must exist and be positive for even very small theta values, that means I must, as I come down to 0, come in at it from the right. And the r is going to get bigger and bigger very fast. I'm going to have some kind of spiral. And if I consider negative theta values, it'll come in the opposite direction. And I think there's going to be some kind of symmetry that I'm not really good at graphing freehand. But like, whatever it's doing this way, it's going to do the same thing the other direction. Actually, wait, no. Have I messed this up? I want to think about a negative theta value is giving me a positive number. Oh, this is one of these cusp things, just like the cardioid had. So this is coming up off of 0, too. So I think we have an up-down symmetry. But these are going to keep going around forever and ever, bigger and bigger, faster and faster. You graph a couple of these things, you see this is very different from r equals theta, which I think will have a left-right symmetry, but they're still just big spirals. As theta increases, the r is going to get bigger, faster and faster. You swing around. Let's think about... So, key thing to keep in mind that I was saying, this is a version of a parametric function. Remember, a parametric curve, which we already talked about how to do all the calculus of, arises when I have a formula for x as a function of t or y as a function of t. Well, it's really easy to write my x as a function of theta, because remember, x is just r cosine theta, y is just r sine theta. If I have a formula for r in terms of theta, which is the usual way of graphing a polar coordinate graph, you're going to end up with, like, sticking that into here becomes x equals theta squared cosine theta, y equals theta squared sine theta. If I wanted to do calculus on a polar coordinate curve, the fact that I already know how to do it for a parametric curve answers most of my biggest questions. I know how to find the area between the curve and the x-axis or the y-axis. I know how to find the arc length. I know how to find the slope. I know how to find dy dx or d squared y dx squared. All the stuff that we just did for parametric, I automatically get all that stuff for free for polar. A couple key things to note. Okay, let's do an example. Let's find what's the slope of this. Let's find what's the equation of the tangent line. at theta equals, let's make it pi over 4. Let's make it pi over 2. I drew it so it looks like it's horizontal, but I think it's not actually horizontal because the r is increasing, so I think we should get some negative slope here. How do I find the equation of a tangent line? I think back to what I knew about parametric curves. I need the slope. I guess I need the x value and the y value. X is r cosine pi over 2. What is r? R is pi over 2 squared cosine pi over 2. What is cosine pi over 2? Is that 0? Yeah, that's 0. Okay, yeah, I knew the x coordinate was 0. Duh. Y is r sine pi over 2. Sine pi over 2 is 1. R is theta squared. So I get pi squared over 4. So my coordinates of this point are 0, comma, pi squared over 4. My rectangular coordinates of the point. If I have multiple, if you have multiple coordinate systems floating around, it's a good idea to label your x, y coordinates as, hey, by the way, I'm talking about an x and a y, not a theta and an r. How do I find dy dx? The way you did it in parametric was you found dy dt divided by dx dt. Here, that's derivative of y with respect to theta over dx d theta. I can do that for these things. I guess before I do it for this particular one, I'll write out the general formula. If my x is some function r of theta, cosine theta. So if I have r equals r of theta, and I want to find what's dy dx, the thing that's motivating me is that x is going to be that function of theta cosine theta, y is going to be that function of theta sine theta, dy dx is going to be dy d theta over dx d theta. Is going to be, how do I take the derivative of y with respect to theta? Here's my formula for y. I got to use the product rule on this. Derivative of the first is dr d theta. Leave the second alone, sine theta. Plus r of theta. Derivative of the second is cosine theta. On bottom, I need the derivative of the x. Derivative of x is dr d theta cosine theta. Plus, leave that alone, derivative of that, I get a minus from derivative of cosine. Minus r of theta sine theta. There's a good chance your calculus book has this in a box, like it's something to memorize. I generally think this is... You don't save anything from having memorized this. Like, what you did was you did the product rule for me, and I already know the product rule. Hey, I sure hope you know the product rule if you're in Cal 2. So I don't think it's worth having that as a thing to memorize. You can if you're crazy about memorizing things. I'm just, whenever I'm in this situation, I'm always just going to take the derivative with the product rule raw, because, you know, I learned the product rule. I should get some value out of it. Derivative of the bottom thing is derivative of y is going to be 2 theta sine theta plus theta squared. Derivative of sine is cosine theta. Derivative of x is going to be 2 theta cosine theta plus, leave the first part alone, theta squared negative sine theta. I feel like the main thing you get from memorizing the formula is remembering that it's going to be a minus in a second, not a plus. So if I want dy dx at theta equals pi over 2, I need to plug all that junk into there. Cosine pi over 2 is 0, so this thing's going to go away and this thing's going to go away. Oh, that's nice. That means the sine thetas are going to cancel. So I'm left with 2 theta over negative theta squared. So I get negative 2 over theta as negative 4 over pi, right? Huh. That's my slope. So to write the equation of the tangent line, a line is y equals y value plus slope x minus x value, and I have all of these worked out. It's y equals, my y value is pi squared over 4. Plus the slope is negative 4 over pi. I knew it was going to be negative, and I thought it was going to be not that big. 4 over pi is not that big, that makes sense. x minus the x value was 0. If we did this right, it should look right. Let's change this into theta squared. Do I have a caret? Do you have a caret? Oh, there's a squared. Theta squared. We're only looking at the positive ones, that's fine. I just said that the tangent line should be y equals pi squared over 4. Okay, that's the right y value. That's a good sign. Plus our slope was negative 2 over pi. X minus 0 is just x. Something is wrong. That is not a tangent line. Did I remember the number wrong? It's 4 over pi. That's a good sign. Let's change that to a 4. It's not worth it to get the backspace. I'll change it to a 4.0002. That's close enough without needing a backspace key. Yeah, looks tangenty. Cool. We did the tangent line right. We could do all the things we did in parametric, and those parametric versions, I had you compute the second derivative and use that for a second degree Taylor polynomial. You can do that here, but it means needing to take the derivative of this. I'm probably not going to ask you to do that unless this thing has some miracle simplification. This thing did have a bunch of miracle simplification, but only at theta equals pi over 2. So we can't really use that to take the derivative again. We'd have to take the derivative of the giant quotient rule thing. There's tangent lines, and by extension, second derivatives and third derivatives, although they are a pain to compute, and I'll only ask you to do them if they simplify miraculously. Let's talk about arc length in polar. I just made a big deal about how you can write down a formula for slope in polar, but it's not any better than just using the idea of slope parametrically and applying that to the polar context. For arc length, there is a miracle of simplification that happens, though, that totally makes this worth learning the deal. The arc length formula was the integral of the square root of dx dt squared plus dy dt squared. And you integrated with respect to t. In our context, x is some function of theta. I'm assuming r is some function of theta floating around that I don't know what it is yet. So x is that function times cosine theta. Y is that function times sine theta. I want dx dt and I want dy dt, and then I want to square them and add them up and take the square root. Dx dt, well, it's dx d theta, our t thing is theta here, is derivative of the first. I'm just going to call that r prime because I'm going to be writing it a bunch. R prime of theta, cosine theta, plus leave r alone, derivative of cosine is negative sine. Dy d theta is r prime sine plus r cosine. And keep in mind, all of these r's I'm writing down are not variables. They are some function of theta that I don't know what it is right yet. So I want the square root of those things squared. Let's square them first. Dx d theta squared is, when I square this out, I get r prime squared cosine squared. Double the cross term is minus 2 r prime r sine theta cosine theta, plus the second term squared, r squared sine squared theta. What's dy d theta squared? I want to square this binomial. I get the first term squared. Double the cross term is plus 2 r prime r cosine theta sine theta, plus the second thing squared, r squared cosine squared theta. If I add these together, hey, here's our first miracle. Those things cancel. Dx d theta squared plus dy d theta squared is, I get this plus this is r prime squared cosine squared plus r prime squared cosine sine squared. I get a cosine squared plus sine squared. Hey, that goes away. Plus I get r squared sine squared and r squared cosine squared. Hey, that thing goes away. I get just dr d theta squared plus r squared. So arc length in polar is going to be the integral from theta 1 to theta 2, whatever the theta values your functions are on, of the square root of dx d theta squared plus dy d theta squared just turned out to be dr d theta squared plus r squared. This is so much simpler that it's worth memorizing this one. Hooray. So I can work out the perimeter of a circle. I think we already did that when we were doing just regular parametric curves. We did the perimeter of a circle, and it's the same deal here. Same deal as regular arc length. There's a good chance that if you grab a random curve, this integral turns out to be really hard. Integrating the square root of something tends to be a difficult integral, but sometimes it's doable. If I wanted to do that cardioid, actually I'm not going to try and do that. If I try and make up a problem, it'll go bad. Do I have a... Yeah, I'm not going to do an example of arc length. That's the formula. If you guys have questions, I can help you with the ones in the homework. Let's talk about area. The way we did area in parametric curves... Ooh, I have a picture I want to show you. I thought of this in bed last night. It's a really good... Alright. When you do area in parametric, you usually have two options. Let's pick a simple example where I have my x-coordinate is positive and increasing and my y-coordinate is positive and increasing. Here I have x equals x of t, y equals y of t. There's some x-coordinate function and y-coordinate function going on. If I wanted the area between the curve and the x-axis, let's call this the green area, the red area. This area is going to be the integral from a to b of y dx, which means here the integral from a to b of y of t times x prime of t dt. That dx becomes dx dt dt. I'll write it as dx dt dt. Or I could do it the other way around. Like, there's nothing special about y being the y value and x being the x value. If I switch the x and the y, instead of getting the area between the curve and the x-axis, I could get the area between the curve and the y-axis. Like, I can just rename which one was x and which one was y and spin the picture around if that makes me feel better. But it's not anything deep to say this area is the integral from a to b of x of t dy dt. It's the integral of x dy, which would be, if we had the letters x and y switched, would have been how you integrated how you found all the areas in your Cal 1 class was, instead of integrating y, you integrate x with respect to y. So integrating x dy becomes this thing. Hey, I think it is worth noticing the integral by parts formula. The integral by parts formula says the integral of y of t times x prime of t dt from a to b. According to the integration by parts, if I use u equals y and dv is x prime, then du will be derivative of that as y prime, and v will be x. According to integration by parts, this is going to be equal uv is x of t y of t minus the integral of v, x of t, du y prime of t, dt. The integral had a bound on it, so this is from a to b, and this is from a to b. Well, the left-hand side here is the red region. And this thing I just said is the green region. What is this? This is x times y evaluated from b to a. That'll be x of b times y of b minus x of a times y of a. X of b was the x-coordinate of this point. Y of b is the y-coordinate of this point. If you multiply that x-coordinate and the y-coordinate, you get the area of the big rectangle minus the area of the little rectangle. So, we get, the integral by parts formula tells us that the red thing equals the whole L-shaped thing. That's what I get if I take the big rectangle minus the little rectangle, minus the green thing, which sure enough geometrically it is. Cool. I never saw such a visual interpretation of integration by parts. And you it's the sort of thing that falls out from having a parametric thing. And it's sort of neat to think about how, if you, like, this happens in some geometrical situations. If you want to integrate, like sine inverse, if you wanted the integral of that from 0 to 1/2, it's likely to be doable by saying, hey, wait, I know how to integrate sine. Let's integrate sine, and then subtract that from something. The way you integrate sine inverse x is to use integration by parts, which will turn out to be something like that. It's like geometric circumstances where switching the parameter, switching the x and the y turns a function that's hard to integrate into something that's easy to integrate. And working the integral out that way is basically what integration by parts does. Okay, that's my pretty integration by parts picture that I like. We talked about arc length. I wanted to okay, now to talk about area. The thing about area in polar coordinates is most of the time, let's find the total area of the cardioid. It was r equals 2 cosine theta. Integrating y dx is usually not the best way to do it. This is how we did it in parametric. And I'm sure we can adapt it to work with polar, but most of the time you don't really want to do that. Instead of doing that, the traditional thing you do when you're finding area in polar is, instead of thinking about translating it to x and y, you think about what is the area swept out. Like, don't look for the area between the curve and the x-axis. Look for the area that is swept out by all that polar stuff. Like, I want to integrate from theta 1 to theta 2, and I want my integral to somehow catch all the area swept out by a polar curve. So, doing it this way, this would give the area below the, like for that example, instead of getting that, I'm going to get this. The area between the curve and the x-axis, because that's what the integral of y dx gives us. For most polar things, like I guess for the cardioid that we were talking about, that'll be kind of the same thing. But this formula is by and large just easier to work with. How would we work out this area? I want to think about a tiny delta theta value. I want to pick a tiny little delta theta and say, how would I work out? I have this r value, r of theta, let's call it, I want to call it theta, let's call it theta 0. And here's r of theta 0 plus delta theta. I'm thinking about, I took some specific value and some specific very nearby value, and I want to try and estimate what is the area of this little wedge. The key thing going on is this little wedge, because my two r values are going to be close to each other, is almost a part of a circle. How would I find out the area of a part of a circle? Well, think about it like it's a pie graph. I have delta theta is the angle that I've used out of 2 pi of the entire circle. So this is the proportion of the circle that we've got. So the area is about that proportion of the area of the whole circle. The area of the whole circle would be pi r squared. Which r value should I use? Should I use the first r value or the second r value or one of the r values in between? That's the type of choice that you make when you're doing a Riemann sum about should I use a left-hand Riemann sum or a right-hand Riemann sum. And the thing you learn when you're doing integrals is they will all converge to the integral. Maybe one is more accurate, but your choice of r value that you pick doesn't matter here. This turns into 1/2 r squared times delta theta. Adding those up, you get that the area swept out by the curve, by the polar curve, is the integral from theta 1 to theta 2 of 1/2 r squared. The delta theta becomes the d theta that you're integrating against. So let's write this out. In polar, the area swept out by r equals r of theta between theta 1 and theta 2 is the integral from theta 1 to theta 2 of 1/2 r squared d theta. How hard is that to integrate? Depends on how hard your r of theta function is. So I've got the curve r equals r of theta, and I'm thinking about what is the area swept out between those points and the origin. Like, this is the most natural way of measuring area in polar coordinates, and this is the formula for it. Note that this assumes that the area doesn't overlap on itself. Like when I had the r equals 2 cosine theta, and going from 0 to 2 pi would give the entire circle twice. If I do the integral from 0 to 2 pi of 1/2 r squared here, that'll give double the area. Because when I go from 0 to 2 pi, I'm going to get this area, then this area, and then, so that was 0 to pi over 2, then pi over 2 to pi. Pi over 2 to 3 pi will give this area again, and then 3 pi over 2 to 2 pi will give that area again. You end up sweeping the whole thing twice, so you will end up getting double the area. That's a thing you have to watch out for in polar, is your r, like sometimes the function repeats itself, and you want to make sure you're only getting a chunk of it. The area of the cardioid, r equals 1 plus cosine theta. That's one we sketched just a second ago. Looked like this. It doesn't repeat itself. Going 0 to 2 pi will give us all of it exactly once. Is the integral from 0 to 2 pi of 1/2 r squared. How hard is this to integrate? I gotta FOIL that out. 1 plus 2 cosine theta plus cosine squared theta. And I guess we don't actually care what the number is. You do this integral. To integrate cosine squared, you need to rewrite it as 1 plus cosine 2 theta over 2. Cool. That's area in polar. Oh, I should do an example like this one. Here's a question. Can we write the cardioid in Cartesian coordinates? Our cardioid, the way we wrote it, was r equals 1 plus cosine theta, right? You can put a sign there instead, and you'll like rotate the cardioid some direction. It'll have the same little pinchy heart thing. How would we do that? Just a second ago we saw that converting cosine theta into Cartesian is a pain. I'd rather multiply both sides by r. If I multiply both sides by r, I should be a little bit suspicious. Have I introduced the extraneous solution r equals 0? R equals 0 is just 1 point the origin, which is already on the cardioid, so I'm not adding anything here. I get this. I kind of want to think about r squared equals r plus r cosine theta. If I converted this right now, I would get r squared. I can do that easily. That's x squared plus y squared. R cosine theta I can do easily. That's just x. What does my r turn into? My r will be plus or minus the square root of x squared plus y squared, which is a pretty ugly formula. And I would need to figure out, is it the positive one or the negative one? I guess in all of our circumstances, our r value is always positive, so it would always be the positive one. So yeah, here is technically a I can pick the positive because if I go through quadrant by quadrant, I can check my r thing is always positive for 1 plus cosine theta. 1 plus cosine theta is always positive, so r is always positive. This is sort of an unsatisfactory equation because it's got the square root in it. If I wanted to make this about a polynomial equality, it would be, let's move the x to the other side and square it to get rid of the square root. It might be better to do that over here in the polar version of the thing. So r squared is going to be that thing squared. I guess that doesn't save us much. I get that x squared plus y squared equals x squared plus y squared minus x squared. Ugh. If I'm hoping to write this in function notation, I want to like figure out how to solve this thing for y. Is this a thing I can solve for y? I guess let's FOIL out the left-hand side. X to the fourth plus y to the fourth plus x squared plus double every cross term will be x squared minus x is minus 2x cubed. X times y squared I get minus 2xy squared. Y squared times x squared I get plus 2x squared y squared. It's supposed to equal x squared plus y squared. Let's move everything to one side. Are there any... Y is only squared, isn't it? Huh. So if I group all the y squareds together on one side and all the x junk on the other side, I can solve for y squared. This isn't actually as bad as I thought it was going to be. Okay. Y squared, x squared cancels with that. I can just clear those out. That's even easier. So I got x to the fourth minus 2x cubed minus y plus y squared times 2x squared minus 2x. I guess I get that y squared is... Have I done this right? I'm very suspicious that y is only ever squared. I guess that makes sense because there's a vertical symmetry to the thing. Y squared equals 2x cubed minus x to the fourth divided by 2x squared minus 2x. There's some x's here I can cancel. If I reduce by 1x, I get 2x minus 2 on bottom. I get 2x squared minus x cubed on top. I get y is plus or minus the square root of that thing. Yeah, something has gone wrong here. Because I'm only getting 2 values. And for certain x's, there are up to 4 different y values. So, I've screwed something up. Why don't I look at my notes? That's why I made my notes. That's what I did wrong. This was not supposed... okay. Do I want to fix this? Yeah, let's fix this. This is worth carrying through to the end. When I FOILed out my y squared, I didn't get a y to the fourth. I only had y squareds. When I square the y squared term here, I should have gotten y to the fourth, and I wrote y squared instead. I guess I can... Well, I don't want to undo and show it off. Let's try this again. FOIL this out. Square the first term, x to the fourth. Square the second term, y to the fourth. Square the last term, plus x squared. Double the cross term, 2x squared y squared. Double this cross term, minus 2x cubed. Double this cross term, minus 2xy squared, equals x squared plus y squared. Okay. This can cancel with this. Let's move the y squared over. This time I'm going to move everything to the left, and I'm going to group it by powers of y. I have one y to the fourth. I have some y squareds. How many y squareds do I have? I have 2x squared, y squared, minus 2x y squared. When I move this to the other side, it'll be minus 1 y squared. Plus, what's the stuff that doesn't have any y's on it at all? It's x to the fourth minus 2x cubed. Cool. This makes more sense. When does this equal 0? Hey guys, this is a quadratic. I can solve a quadratic. You want something squared plus a multiple of that something plus a constant to equal 0? The solution to that is, it's a quadratic in y squared is opposite of b plus or minus the square root of b squared minus 4ac all over 2a. So y by itself is plus or minus the square root of that. Gross. This makes more sense. I have the two plus or minuses, so I will have up to 3 solutions. I will have up to 4 solutions. Sometimes this thing will be negative, sometimes it will be taking the square root of a negative, so things won't always all be there. But I get up to 4 solutions. Weird. I guess if I graphed these 4 things, they will give me the 4 branches of the cardioid. Interesting. We might be getting extra stuff because we squared both sides of an equation. So multiplying by 0 can introduce extraneous solutions. Squaring both sides can also introduce extraneous solutions. I'm not sure what happens if you graph those 4 things. I'm a little bit curious. Not curious enough to try and type it all in right now, though. So there's just one example to show off how gross this is. Yeah, that was over an hour. Let's call it for today. I'm going to be doing shorter lectures because this stuff is way easier. There are way fewer examples needed. Do I have the homework up? You can now do everything through arc lengths, everything through 152. Go do homework through number 152. Have a good weekend. I'll see you guys on Monday. Oh, I should talk about timing for a second. I think we're probably on track to have our exam this coming Friday. There's only a couple more days of material to cover. I guess I'll talk about that when we're actually closer. Cool. See ya. Live stream off.